In this video, we are going to solve some more equilibrium problems, continuing on from 13.6 in your textbook. So I want you to consider the reaction with 2HF reacting to, or decomposing to form hydrogen and fluorine. We are given our equilibrium constant to be 1.0 times 10 to the second at some very high temperature. In an experiment, 2.50 moles of HF and 2.50 moles of hydrogen and 2.50 moles of fluorine are mixed in a 5-liter flask and allowed to react to equilibrium. For the equilibrium, solve for the equilibrium concentrations. So, calculating what that initial concentration is from what we're given 2.5 moles and we have 5 liters. So that's going to give us an initial concentration of 0.500 molar HF, 0.500 molar H2, and 0.500 molar F2. So, because we have initially both reactants and products present, we don't know which direction this reaction is going to shift. So that means that we do need to solve for Q in order to set up our Rice table. So what that means is we're just going to plug in these initial concentrations that we calculated into our reaction quotient. So remember, it's your products, hydrogen and fluorine, divided by your reactants raised to the power of the coefficient. And since we have 2HF, HF is going to be squared. So that's going to give us 0.5 times 0.5 divided by 0.5 squared, which is going to equal 1. So now, when we look at this, Q is 1, and K we said is 1.00 times 10 to the second. Q is just 1.00, so that means that K is greater than Q, so this is going to shift to the right. So because K is greater than Q, the reaction shifts to the right. So now we can set up our Rice table because we know which direction the reaction is going to shift. So here I just put in the reaction from the problem above and then the initial concentrations that we calculated here from what we were given in the problem. So now we are going to look at the change, and so we are shifting to the right, so that means we are going to lose reactant and we are going to form products. So this is going to be minus 2x, and that 2, remember, comes from the 2 coefficient, and then this is going to be plus x, 1x, just because we only have one of those, and then plus x for F2. And then at equilibrium, this is going to be 0.500 minus 2x, and this is going to be 0.500 plus x, and this is also going to be 0.500 plus x. So now we need to solve for the equilibrium concentrations. So I'm going to write the K expression for this problem. So K is equal to the concentration of hydrogen times the concentration of fluorine divided by the concentration of HF squared. And we are told that this equals 1.0 times 10 to the second. I'm actually going to change that. I mean, that is what it equals. I'm just going to try to get this all here on one line so I have more room to solve. Okay, so now I'm going to plug in the equilibrium line into the K expression. So we have 0.500 plus X for hydrogen. We also have that for fluorine, so I'm just going to square that, is equal to 0.500 minus X, and that is squared, and all of this is equal to 1.0 times 10 to the second. So this is another case of a perfect square, which we like perfect squares because they make our life a little bit easier. So I am going to take the square root of both sides. That's going to leave us with 0.500 plus X divided by 0.500 minus X is equal to 1.0 times 10 to the second is 100, and the square root of that is going to be 10. So now I just need to solve for X. So I'm going to have 0.500 plus X is equal to 10 times 0.5 is 5. 10 times minus 1x is going to give us 10x. Is that right? Oh, this should have been 2x. I'm sorry. Missed that. So this is going to be 20x. So minus 20x. 2 there. Okay. So okay, so now we just need to solve for x. I'm going to add 20x so this is going to give me 21x is equal to 4.5, and then divide by 21 on both sides. So x is going to be equal to 0.21. So now I know what x is equal to. So now I can solve for my equilibrium expression. So the concentration of hydrogen is equal to the concentration of fluorine, which is equal to 0.500 plus x which this is going to be 0.710, and then for HF is 0.500 minus 2x is equal and that is going to be equal to 0.080. Okay, so the negligible x. So this is what happens when you don't have a perfect square. When solving an equilibrium problem, some plus x and some minus x values can be treated as negligible, meaning that they're really, really small. So x is considered negligible if it's less than 5% of the number that it was to be subtracted or added to. The value of x is considered negligible when the value of k is very small. If k is small, very few products are formed, so x is going to be a very small value. For most of the problems you will encounter, x will be negligible, but always check your answer to make sure it makes sense. So here we have gaseous NaCl that decomposes to form nitrogen monoxide and chlorine gas. If 0.650 moles of NaCl is placed in a 2-liter flask, what will the equilibrium concentrations be for each species in the reaction? And K constant is 1.6 times 10 to the negative fifth. So to figure out what the initial concentration for NaCl is, I'm taking my moles and I'm dividing it by my volume. So then my rice table, NaCl is decomposing into NO and chlorine, and there it is balanced. So we know what the initial concentration is only for our reactant. We don't know anything for nitrogen monoxide or chlorine, so we're going to assume 0. So now, looking at the change, we're going to shift to the right, so minus 2x and plus 2x, and then plus x, and then our equilibrium. So the K expression, we've been writing these, so I just have that. There is nitrogen monoxide concentration squared times the chlorine concentration divided by the nitrogen, or NaCl, which is also squared. And so I plug in the equilibrium line into the K expression here. And solve this down a little bit further. So we're going to get 1.6 times 10 to the negative fifth is equal to 4x squared times x divided by, this is going to give us 0.106 minus 4x squared. And 4x squared times x is actually going to give us 4x cubed. So I'm just going to write that in here so I can show you what this negligible x is all about. Just kind of simplifying it a little bit. So you will notice that the power for x on the top is not equal to the power of x on the bottom. So when this happens, you're going to find wherever your x is added or subtracted, and you are going to say that that is going to be such a small amount that that is not going to have much effect. So we're just going to cancel this out. So that's going to give us 1.6 times 10 to the negative fifth is equal to 4x cubed over 0.106. And then solving for your x from there. So I got 1.7 times 10 to the negative sixth is equal to 4x cubed divided by 4 divided by 4. This is going to be and then take the cubed root of both sides, and x is going to be equal to 0.0075, and then we can solve for our concentrations from there. So go ahead and actually solve for your concentrations. I'm not going to have enough time to show you that in this video though, but what I wrote here you will be able to solve it.